Nice crowd today. How you guys doing? Okay, so we'll get started today working with chapter 6. So chapter 6 deals with estimation methods. We'll talk about section 6.1 today, which is one of those methods called the maximum likelihood estimation. On Monday next week, we'll talk about another method, section 6.2, which is the method of moments, and kind of talk about some properties that we can use to compare different types of estimation methods. So the name of the game today would be just to focus on one of those methods, which is the maximum likelihood estimation. So before we get going, I just want to let you know that I put up a homework assignment. There's nothing due Monday. You guys just had an exam and we just had one class today. So the next exam is going to be due the following Monday. Just so you know, since we don't have homework next week, it is a bit longer than some of the other ones. I mean, it's not like 20 questions long. I think there's about 10 questions on it. So just don't wait until Sunday before it's due to do them. I would say the first two problems on that assignment you should be able to do after today. So I would definitely encourage you to start working on the first couple of problems over the weekend. Any questions about things before we get started?
When are we going to be able to see at least the multiple choice part of the exam?
I will let you guys know once I publish that. I'll
Okay.
get it up by the end of the week.
All right.
Okay, so let's kind of pick up with some of the motivation that you guys just quickly watched before today's class. So the example I want to start with, so kind of the whole point of this section or this chapter is, finding the appropriate statistical model for a situation is probably one of the most critical things that a statistician does. So you collect some data and then you want to figure out, well, what is the best model that's going to fit this data? And it's a complicated question and there are different methods for doing that. And so first we'll talk about this method, maximum likelihood estimation. But the idea is, for example, if we are thinking about slot machines and like how frequently they pay out jackpots, and we don't know what the model is for how many jackpots are paid out on average over a week span. So we collect some data to try and figure out what that model might be. So here the idea is each of these values of X is how many jackpot were paid out by that slot machine over a week. And so this would be, okay, one slot machine was chosen at random. It paid one jackpot out over the week. This one paid 3, this one paid 4, this one paid 8 jackpots. And then we might look at this data and say, let's find the statistical model for the distribution of jackpots paid out by a randomly selected machine. So kind of the process here is like a two-step process. One would be to think, like, what model do you think this fits? And then secondly, so that's kind of like what family of function do you think we're in? And then let's find the parameters of that function. So it's really not all that different than, if we think about this from like a functional point of view, if I gave you a data set that looked like this and said, hey, find a function that models this data, you might start to think like, oh, I think y equals x squared makes sense. And then you might think about, okay, well, how can we find that parameter k that's going to fit this data best? So that's essentially what we're doing right here as well. We're first thinking, what is a model that makes sense? And then let's use the data to figure out what are likely values for the parameters in that model. So some models have more than one parameter. Some just have only one parameter in them. So that's the goal here. So the idea is we've collected this sample, and we would like to know this sample came from what population? What's a model for the population? So kind of the first step would just think about what model fits the data, and that might depend on your like practical understanding of models and what this data set looks like. So for this example, using a Poisson distribution probably makes sense for a number of reasons. First is this is a discrete random variable, right? Because we're counting things as opposed to measuring things. So we're counting how many jackpots were paid out in a week. So I wouldn't want to pick a normal distribution or an exponential distribution or things like that because those are continuous random variables. And the reason there are different types of discrete distributions, binomial, geometric, we've talked about other ones. The reason why a Poisson might work out here is Poisson distributions are used in situations where the most frequent occurrence are smallest values, and as x gets larger and larger and larger, the likelihood of x being large gets smaller and smaller and smaller. So if you think about watching a slot machine, right? You can't just go and pay out 4 jackpots a week unless you've already paid out 3 jackpots a week, right? So what's happening is as the number of jackpots is getting larger and larger and larger, it's really not that unlikely that it's going to pay out 1 jackpot. It's a little less likely that it's going to pay out 2, and then even less likely to pay out 3. So as x gets large, what's happening is the probability that x occurs is getting smaller, right? So it would be less likely to pay out 12 jackpots than it would be to pay out 11 jackpots because you would have to pay the 11th jackpot before being able to win the 12th jackpot. So when a distribution has, you know, the bar on the left is biggest, and then as we move to the right, the bars are getting smaller and smaller and smaller, that's where a Poisson distribution would fall. So any questions about where the Poisson distribution came from in this example? Okay, so we're gonna kind of do this estimation approach today from a very theoretical point of view. So we're gonna use functions, and we're not gonna need to use end calculus. We're gonna use some derivatives, and we're not gonna be using R or simulations for this. So the PDF for a Poisson distribution is given over here. And when we write out these probability distributions, just to be clear, we have 2 things here. X is denoting random variable, and it takes on different values depending on, you know, what slot machine is picked or what's picked from the population. Lambda, this is called a parameter. And okay, its value is fixed. It doesn't vary. And for a Poisson distribution, here's the PDF. And here, lambda is denoting the mean number of jackpots in 1 week. This is a factorial over here. So now I would like to figure out, okay, what is the value of lambda that best fits this data? So far we figured out my model is going to be Poisson. That comes from just informally thinking about the situation. Now I've got my data. Now I want to think about what is the most likely value for lambda if this is the data that I got from a sample. So what we can do first is to write out what's called the likelihood function. So let me just, we could first think about, well, what is the probability that x1 would equal 1, x2 would equal 3, x3 is 4, and x4 is equal to 8. And first thing is, because we assumed that each of these observations was independent of the other, then the product that the probability that x1 is 1, x2 is 3, and x3 is 4, and x4 is equal to 8 is the same thing as taking and calculating each of these probabilities separately and then multiplying them together. And again, this first equation is coming from the fact that each of these xi's are independent from one another. In general, we can't just do this, right? We would need to think about some conditional probabilities. But because these are independent, we can break them up. And now I've got a formula for each of those probabilities. So with a discrete distribution, if I want to know what is the probability that x1 is equal to 1, I evaluate the PDF at x equals 1, right? Because the PDF tells me what is the probability that x equals this particular number. So I can go ahead and plug in 1, and I'm going to get lambda to the first power e to the minus lambda over 1 factorial. Okay, all I'm doing for that one is just plugging in 1 for x. And that gives me the probability that x is 1. And then I can do that for the others. So what would be the probability that I would get x is equal to 3? Well, that would be lambda cubed times e to the minus lambda all over 3 factorial. And for x to the x3 equals 4, the likelihood of that happening would be lambda to the 4th e to the minus lambda over 4 factorial. And then finally, lambda, the last value we had was 8. And what that formula tells us is what is the probability of getting our sample from some Poisson distribution with parameter lambda. And we don't know what that value is yet. So we're going to use this to figure out what's the most likely value for lambda. But any questions? Okay, so this function that we have up top, let me simplify this. And I will write it like so. So if I take this formula that I had up here, which was the probability of getting our sample, I'm just going to do some algebra here and just group these terms. So for the lambdas, I have lambda to the first, third, fourth, and eighth. So let's see, if I add those up, I get a lambda to the 16. And then I've got e to the minus lambda times e to the minus lambda. I have 4 of those. So that gives me e to the minus 4 lambda. And then I can divide all of that by this product. We can write that out like this. So in this case, this is what we would call the likelihood function. We oftentimes will just write it in terms of being just a function of the parameter lambda. So sometimes you might see it written as a conditional probability, and that's what this vertical bar is referring to, is a conditional probability. So just to kind of connect these ideas, right, we assume that this is coming from a Poisson distribution with undetermined value lambda, with undetermined parameter lambda. So we want to figure out what lambda is. So regardless of what lambda is, this formula over here tells us if we pick this data from a Poisson distribution, this would be the probability of getting 1, 3, 4, and 8. And now what I'm doing down here is I'm thinking of this formula as a conditional probability. Given that we picked this sample over here, this likelihood function, what this output is telling me is what is the probability of getting this sample. And so what we're going to do to find the best model is we're going to pick the value of lambda that makes this probability greatest. That's going to make this likelihood function take its biggest value. So now when we think about this likelihood function, it has an input, which is lambda. And the output is going to be the probability of getting our sample for that given lambda value. So what I've done over here, right, if you're looking at this function, it's just a function of one variable. It's like a very single variable calculus sort of thing. So what I want to do is I want to find the value of lambda I'm going to find the value of lambda that's going to make the sample that we observed most likely, right? That's going to make that probability greatest. And right, if we had the graph, well, then it's just like a visual thing. I could say, okay, that if I set lambda equals 4, that's going to give my sample the maximum likelihood of occurring. So we can see that this likelihood function, just looking at it visually, takes its greatest value at lambda equals 4. So we'll talk about how we could do this more precisely if we didn't have the graph. You might recall, like, we can find global max, taking the derivative, setting the derivative equal to 0, and going about it that way. So that's what we'll be doing in a second. But I just wanted to, without the calculus yet, just kind of show you what the process is, and make sure, I think what you really want to make sure now, and if it's not clear, and now's the time to talk about it, that you understand what this likelihood function is measuring. That's the key ingredient in this process for the MLE. And this value lambda that we just found, it's an estimate for the actual value of the parameter. So that's why it gets a hat. So it gets the same old hat that all of our estimators get. And this is a very special type of estimate. So we put a subscript on it that says MLE to denote that this is the maximum likelihood estimate for lambda. Okay, any questions? Okay, so kind of one nice thing about this section is it is very much like algorithmic process. You know, step one, do this, step two, do that, and so on. So the first step in the process of doing this maximum likelihood estimation is finding the likelihood function. And the likelihood function is going to be the product, since we're assuming that we're picking these samples independently. It's just going to be the product of the PDF function at each value x in your sample. And so this is true. We should just be careful about like what happens when we have discrete versus continuous distributions. So far, this is regardless of whether we're continuous or discrete. So this would be the same. We would get the likelihood function the same way. So down here, we actually have an example, one of which is continuous and one is discrete, just so we can see the difference in what these might look like. So binomial distribution, that's discrete. We're counting how many successes. Exponential distribution, that's continuous. We're measuring the length of time between occurrences. Okay, so for a binomial distribution, if we're going to find the likelihood function, which is what this is asking us to do, right, then we need to know what the PDF is. And here, our parameter is P. Since we have a fixed number of trials, where we have 3 trials here. So the idea here is you're repeating something 3 times and you're counting the number of successes that you get. And so the idea is we did this. The first time there was 1 success. The second time, all 3 were successes. All 3 were successes. And then on the 4th sample, we got 2 successes. And so now we would say, based on the number of successes that we got out of all of these trials, what do you think the value of P is? That's what we're going to try and do. So way back when we were working on stuff on the first exam, when we went through all of these distributions, there was like a nice handy formula sheet where all these things were, that I suggested you create a formula sheet to store all these things. So having some place to refer to for these formulas is useful. But if you don't recall, here was a formula for binomial distribution when n is equal to 3. So typically binomial distributions depend on 2 things. Here we've fixed n and we want to figure out what P is. So here our parameter is P. And we found that in the first sample, there was 1 success. Sample 2 had all 3 successes, as did sample 3. This one had 2. And right, this process we can do no matter how many observations we have. Here we have x equals 4. We have 4 observations. Just gets more time consuming, but the math is the same whether we had 4 or 24 observations. So what we can see above is that we're just going to take the product of these 4 PDFs, right? PDF evaluated when x is 1 times when x is 3 times when x is 3 times when x is 2. Right, so that's what happens for the first one, that x1 was equal to 1. And then we would multiply several copies of that. Okay. So sorry. So this is what I would get when I plug x equals 1 into this formula, right? So I would get 3 choose 1, p to the first, 1 minus p squared. Next, I'm plugging in what happens when x is equal to 3. That gives me 3 choose 3, p cubed, 1 minus p to the 0. The next value, the next sample had the same. And then the last one was x was equal to 2. Any questions so far? So we've got, right, we have 4 things. That's where this times this times this times this is coming from. And now I'm just going to simplify them. So 3 choose 1 is equal to 3. 3 choose 3 is 1. 3 choose 3 gives me 1 again. 3 choose 2 gives me this 3 over here. So that's the product of these 4 numbers that we have. Now I'm going to group all of my p terms together. So I have p to the first, p cubed, p squared. So that gives me 9 p's, right? And then I group together my 1 minus p's, which are 3 of them. And that would be my likelihood function for this one. So if I multiply out my 3 times 1 times 1 times 3, it comes out to 9p times 1 minus p cubed. So this would be the likelihood function for that sample picked from a binomial distribution. Any questions about that? Okay. So next up would be the exponential distribution example. So now this is a continuous distribution, but we're not going to have to adjust anything in our approach. So, well, we do need to adjust our function. Right, so for exponentials, the PDF, at least when we write it in terms of lambda, is equal to this. So just keep in mind right? That parameter lambda in the exponential distribution, that's referring to 1 over the mean. So with exponential distributions, like we're dealing with a fixed time period, like, you know, how many times does something occur? Okay, anyway. So sorry, I had that wrong. What I meant to say is this is continuous. What mu is measuring is the mean time between occurrences. So lambda is 1 over that. And so here, if we wanted to come up with the likelihood function, okay, this is going to be a function of the parameter lambda in the exponential model. So we could write that as the product of all of the PDFs evaluated at each of those xi's. So that means we would get lambda e to the minus lambda x1 times lambda e to the minus lambda x2. So we would do that for all n observations that we have here. So just doing some algebra, we could simplify that, group all the lambdas together, and then add all of the powers of the exponent e together. Okay, any questions about either how we derived those likelihood functions? So, I mean, there's 2 things you need to know, and that is what's the PDF, and that's going to depend on what you're assuming the distribution, the underlying population is. And then it's going to be the values that you observe. So once I know what the PDF is, then I just evaluate it at each of those values and then take the product. Okay, so then we're ready to come to the calculus side of things. So this would be like the first step in the process is finding the likelihood function. So that would be like step 1. And that's what's kind of written down at the bottom. We've got the general process. So it's kind of a 2-step process. We find the likelihood function, then we maximize it. And then maximizing it, right, that's a calculus process. So that means we want to find the critical points and then figure out which of the critical points gives us the global maximum. So after we find the likelihood function, then we're going to take the derivative of it. And we're going to take the derivative of it with respect to the parameter that we're going to try and find. Because again, the goal here is we're going to find the value of this parameter that makes the likelihood function greatest. So in this case, we can take the derivative on this using product rule. So we would get like 81 p to the 8th times 1 minus p cubed. So I'm just going through the calculus kind of quickly here, but that would be the product rule. You certainly could distribute that out and do it that another way if you like to. And then we want to figure out what are the critical points, right? And so these are going to be values of p that make the derivative 0 or undefined. So then it becomes some algebra. So I'm going to just factor 27 p to the 8th times 1 minus p squared out of each of these two terms. So we've got this one. And I've got this one. Okay, so I'm just doing some algebra and some calculus. You might be doing it on your own way. Just let me know if you're not clear with one of these steps. So I'm just taking the derivative, simplifying the derivative so that then I can solve when it is 0, when it's undefined. Any questions about my work here? So this is going to equal 0 then when p is equal to 0 is one possibility. That would make this factor, the first factor, 0. This factor over here tells me p equals 1 and p equals -1. Those are other zeros to consider. And then from the last factor, we have 3/4. So these are our critical points. Okay, then you do once you find these critical points, what I'm kind of doing quickly down here is you would evaluate the original function, the likelihood function, at each of those values of p. So I plug in p equals 0 and I get 0. I plug p equals 1 in here, I get 1. P equals -1 doesn't make any sense because p is a probability, so we don't even, that's not even in our domain of consideration. And then we would consider p equals 3/4. When I plug in that, I actually get something which is a little bit bigger than 1. So then the maximum likelihood estimator would therefore be 3/4, since that is the value of P that maximizes the likelihood function. And what's graphed down below is exactly that function. So I graphed the likelihood function below, and here you can kind of see that it, our calculus matches up with the graph that we're seeing there. We can see that 3/4, 0.75 seems to be the value of P that makes that likelihood function greatest. Any questions? I'll just say, if you think about what happened here, this binomial situation, right? Each of these is asking, like, how many successes did we have when we did 3 repeated attempts of something? So out of these 4 samples that we collected, means, like, essentially what we did here is we ran 12 trials of this event, right? Since again, each one of these is saying we did 3 trials, count how many of them were successes. So we can see out of these 12 trials, we had 9 successes. So it makes sense that our estimate for this was the 9 out of the 12, the 3/4. So it's nice when you do this, you come up with an estimate to just ask yourself, like, does that estimate make sense? And here it does. It makes sense that we came up that most likely P is equal to 3/4 because we did 12 trials and 3/4 of them were successes. So let's just guess P is 3/4. Any questions? This is awesome. I think this is the longest I've gone, just me going, nobody asking anything. So I hope it's making sense. Thank you, Karina, for the thumbs up.
Makes complete sense to me.
Okay, good.
I don't like to answer for other people.
Yeah, so these were not easily polled questions. So the polls work great because that does give everybody a chance to chime in anonymously. Yeah, I can do something. Let me see. Okay, none of our true false questions are working here. We'll just say, I'm just going to ask this. This is asking you about Zoom. Let's just replace synchronous learning in Zoom with, is this feeling good? Yes would be good. Nope is, I've got some questions and I'm just not even sure what to ask. Just want to know where people are at on this. Okay. So we've got 5 okays, 1 saying, I'm not so sure about this. So for the person who's not sure, you're welcome to chat me in something. I obviously don't care. No judgment on me. But if you want to chat something to me, you're welcome to. I'll just see it. We're going to do some more examples. So maybe that'll get cleared up in the next example. But if you do want to ask something before I move on, please don't feel bad about doing so. Okay, so let's try and do one more together, and then I want to give you guys a chance to practice one on your own, or at least in a group before we go for the day. So let's think about how we could find the how we could finish up the process for this one over here, for the exponential distribution. Okay, so we've got our likelihood function over here that we found. Which again, we got by taking the product of the PDFs. And now we don't have actual values for the x1, x2, x3s, and so on. But we're going to treat those as constants, right? So let's assume we have some sample of x's. And really the variable here is lambda. We're thinking about how do different values of lambda affect how likely it would be for us to get a fixed sample that we have. So we kind of think of our sample as fixed, and now we're going to play around with different values of the parameter so that our output becomes most likely. So over here, we would next go ahead and take the derivative of this. With respect to lambda. And let me just say that that's not an easy derivative to calculate. And not only that, after we find the formula for the derivative, excuse me, we would then have to solve like when is the derivative equal to 0. So here's a nice little thing that happens a lot with maximum likelihood estimates. And that is, this is going to be a case where it actually is going to be, in some situations, a little bit easier to figure out when is the natural log of the likelihood function maximized as opposed to the likelihood function itself. So consider the following thing. Right, so that's a natural log function. That's its graph, at least. And so what we can see from this graph is right, natural log is an increasing function. So if the natural log is greater and greater and greater, that must mean the thing that we're plugging into the natural log is getting bigger and bigger and bigger. So with this in mind, if we find the greatest value for the natural log of the likelihood function, so the idea here is we want to find the value of lambda that makes the likelihood function greatest. That's not an easy thing to do. So I'm going to make this comment that, okay, maybe you'll believe me after we do it. Right now, you might be thinking like you're crazy for taking the natural log of something and thinking that that's going to make things any nicer. Maybe you're right. But I'm going to do it. But before I do that, I just want to make sure that it's clear. So what we're trying to do is we're trying to find the value of lambda that makes this thing biggest. So let me instead consider the natural log of that thing. So if I can find the value of lambda that makes the natural log of this greatest, it's going to have to also be the value of lambda that makes L biggest. Right? If you think about it, if there's some value of lambda that makes this bigger, right, then it's also going to make the natural log of that bigger. So the value of lambda that makes L biggest is the same value of lambda that's going to make the natural log of L biggest. That's the main point here. So in some cases, we didn't have to do it in the previous one, but I will say in a lot of examples, before going on to the maximize part, it might be helpful to find the log likelihood function. In other words, take the natural log of your likelihood function. So I'm going to do that down here. We're going to take right? So over here, I just used this property that the natural log of A times B is equal to the natural log of A plus the natural log of B. To split that up. Okay, then we have this property of natural logs that says the natural log of lambda to the nth power, that's just the same thing as n times the natural log of lambda. Yeah, Stephanie.
Shouldn't that second natural log, it should be negative x, not negative lambda? Where you have the natural log of lambda to the nth power plus the natural log of e, shouldn't it be e to the negative x?
That's a lambda. So that came from this formula up here, which came from back over here. So when we did this calculation, maybe my lambdas and my x's look similar.
Yeah, that is what it.
Sorry, yes, it's just missing. They are close to each other. Yeah, that's a lambda. That came from this part over here. Yeah, sorry. So yeah, if you zoom in, you can trust me. That is actually trying not to be an x, and it looks like that.
I started doing little curls at the bottom of my lambdas, so I don't
Yeah,
get confused because I caught myself doing that.
Okay, so that is a lambda there. but inside the sum are the x's. Was there another question, Stephanie, or that's the same one?
No, that was it. I
Okay.
noticed I was copying it wrong also, so we're good.
Okay. So great. So we had this like likelihood function that had this exponential stuff in it. And if you don't believe me, you certainly could go ahead and try and maximize that right away. Just it actually is a lot harder to do. If we just take the log first, this simplifies quite a bit because of this second natural log here, right? The natural log and this e, they're going to undo each other. And all that's left is going to be lambda times the sum of the xi's. So what's going on both in this step and then in each of these is just using some properties of natural logs. So if it's been a while since you've worked with natural logs, that would be helpful to refresh your memory on those because they're going to come up in quite a few of these problems. So we haven't done any calculus, right? This is just telling us this is the log likelihood function. And so by the kind of comments that we had above about, the natural log is an increasing function. So if I can make the natural log of the likelihood function greatest, that's going to also optimize the likelihood function. So here's my log likelihood function. We're going to take the derivative of this, okay, with respect to, I want to be careful here, with respect to that parameter lambda. So remember, our x's, although in this case, right, we're keeping them arbitrary. These x's are typically going to be numbers that are given to you, like they were in this problem over here. So we're thinking about these values of x as being constant, especially when I'm taking the derivative with respect to lambda, we think of x as constant. So when I take the derivative of this first piece, we're going to get n times the derivative of the natural log, which is 1 over lambda. And then when I take the derivative of this piece over here, right, that stuff that I just coded or colored in blue, this is a constant as far as lambda is concerned. So when I take the derivative of this, it's no different than taking the derivative of some constant times lambda. So we're just going to get the sum of the xi's. Since this derivative would be the same as like if you took the derivative of 3 lambda, you would just get 3. So that stuff in blue is just acting like a constant. And then we want to think about, well, what are the critical values here for lambda? And lambda equals 0 would be a critical point, since that makes the derivative undefined. And otherwise, I can solve that this equation for lambda by bringing the summation to the other side and then dividing by n and going about it like that. So we have 2 critical points here. One of them makes the derivative undefined. One of them makes the derivative 0. And so then you would go ahead and say, let me pick the one that's going to make the likelihood function greatest. And so that likelihood function, that was up here. And let me just say, if you were to plug in lambda equals 0, that's going to make the likelihood of this sample occurring impossible. So that would be a bad choice for lambda. Choosing lambda equals this sum of xi's over n actually makes the likelihood function positive, since those are our only two critical values, critical points. We see that, oh no, okay, this seems to be not working, but I have this on my screen, so let me share that. Okay, yeah, so we were, I had a little bit more work on my version over here, but basically got down to this point over here, that we had two, I didn't write the other one out over here, but there were two possible critical values. One of them was 0, which again, if you were to plug this into the likelihood function way up top, this would give us 0. So the only other critical point was this one over here, which gives us the maximum value. So this would be the maximum likelihood estimate for lambda.
When you solve for that equation, what is it supposed to be? N over the sum?
Yeah, that's what I just thought. You're right. I'm fixing that, but you cannot see that. Yes, you're right. This should have been n over the sum of the xi's. I had that the wrong way. That's right. I solved for 1 over lambda. You're right. So that actually gives us the maximum likelihood estimate for lambda. And keep in mind that that sum of xi's divided by n, right? That's just the sample mean. So we're getting something consistent with, lambda usually is 1 over the mean of the population. And what we're finding out here is like this plug-in principle sort of almost works here, that the best estimate for lambda would be 1 over the sample mean, right? As opposed to the population mean. So at least we're getting estimators here that make sense, which is good. It would be really bad to be getting estimates that don't make sense with the data that we have. Okay. So those were 2 examples. So we did an exponential one, and we did a binomial one. And so I just kind of want to summarize those 2 things. And that is, the results that we're getting are results that make sense. That's usually a good thing in mathematics. You don't want to do a whole bunch of fancy analysis and then get results that don't make sense in the end. And along this vein, since I definitely don't want to get into the details of this, but in the video, like the first example talked about, like, if we collected data that looked like it was normally distributed, then how could we fit a model to that? Keep in mind that this method works whether we have 1 parameter, 2 parameters, 3 parameters, and so on. So we could fit a data set to a distribution that has more than 1 parameter, like a normal distribution. And when you do that process, you'll find that the maximum likelihood estimate for the mean of a normal distribution is the mean of the sample. And the estimate for the standard deviation of the population is the standard deviation of the sample. So we kind of get similar things funneling through that. In other words, our estimators make sense. If you want to, this proof is done in the book, and this requires kind of multivariable calculus here because we have more than 1 parameter involved. Okay, but for your purposes, I am not going to give you a maximum likelihood estimate that has more than 1 parameter. So at most, you'll be doing single variable calculus with 1 parameter. So I just want to kind of, we'll get into some of these measurements before we take a look at that last example, but there are different ways that we think about measuring how good is our estimator. We've talked about some of them, like is it biased? But there are other things that you might want to be concerned about beyond just is our estimator biased or not. So I'll just say that maximum likelihood estimators, they have satisfy some really nice properties, such as consistency, normality, and efficiency. We'll talk about some of those properties next time, what they mean when we compare it to other estimation methods. Okay, so I will kind of just leave you guys to work on this one. If you want to try and work on it right now, I want to give you a chance to work on it and not show you how to do it. So if you want to take some time to do it on your own, that's fine. If you want to go into a breakout room and talk to you or myself, that's fine too. I can set that up. I think what I'm going to do is that I'm just going to leave you guys to try 6, and we can chat about it in about 5 minutes to just summarize our thoughts. So I'm going to give you guys just 5 minutes to work on this. And if you have some questions about it, I'm going to open up a breakout room, and I'm going to send Yua into the breakout room, and Yua will be there. And if you guys have some questions, she can help you out. I'll stay in the main room. All right, so we've got 2 more minutes to go. So I'll just give you guys another couple seconds to finish up your thought, and we can go through the solution. Okay, so I will just kind of give you guys a narration through this, and let me know if you have any questions along the way. But the idea here would be, right, we want to find the likelihood function. Then this is a case where you would want to do the log likelihood function. I would say that that's going to be pretty common, that you're going to want to take the log first and then maximize the log likelihood function. So we're given the PDF and we have some values. So the kind of likelihood function can be simplified to theta to the 4th times e to the minus theta. You could simplify those square roots if you want. I just kind of left them alone. And then on the bottom, we have 2 to the 4th power, and then the product of those square roots. So when we take the log of that, or excuse me, the natural log of that, that would simplify here. So we can break up the stuff on top, right? We break up products. So I can think about this. There's an intermediate step here. So here I'm just using the properties of logs again, that when we split up products, we can think about that as the sum of natural logs. When I have the natural log of A divided by B, then it's the natural log of A minus the natural log of B. So this part wound up over here. This part winds up over here. And then this part down here winds up in here when we take the natural log and break it up. Then we use property that we can bring the 4 down. we use a property here that the natural log and the exponential, they're going to undo each other. So what's going to be left is just the power that was up here. So that's where this all comes from. And then I have all this stuff over here. So this is, at this stage, this is the log likelihood function. And now we take the derivative of that with respect to theta. And so the 4 natural log of theta, when I take the derivative, is 4 over theta. When I have theta times this constant, the derivative is just going to be the constant. And this last natural log, it doesn't have theta in it at all, so it's just constant. So when I take the derivative of this with respect to theta, I just get 0. And then we've got 2 critical points, I should say, which are, okay, if theta is equal to 0, that's going to make the derivative undefined. So that's a critical point. And then we have this other critical point when theta is equal to 4 over the square root of 5 plus the square root of 9 plus square root of 9 plus square root of 10. So out of these 2 critical points, this is the one that gives us the maximum value for the likelihood function. So it is the maximum likelihood estimator. And in case you're kind of curious, here's a graph of that likelihood function. Sorry, you're on a bit of a delay. Well, I think my iPad is not syncing up with this, but yeah, I think we got to the finish line just in time. So the maximum likelihood estimator there was like 3.5. And I'll just say on the PDF version of this worksheet on the very bottom, you should see the graph of this. And we're just getting a consistent answer to the graph. That's all I'm trying to say. So here was a plot of that likelihood function. And then let's say, here's the maximum value. Makes sense that it matches our calculation that it's somewhere at about 0.351. Okay, so we are at time. That's the material for section 6.1 on maximum likelihood estimate. Next time, we'll take a look in the next section and talk about the method of moments. So I will put up a little video and quiz for you about the next section in the textbook. And that's what we'll talk about on Monday. So in the meantime, I would say over the weekend, there are 2 questions on the homework that have MLE estimates. So get cracking on those 2 problems. Otherwise, have a nice weekend. I'll let you guys know once the exams are finished up. I'll get them done before Monday. And yeah, and I'll see you guys on Monday. Take care.